talking, and then I won't start with the actual hands-on part for a few seconds so that people can get here. But I just thought I would show you this theorem from Amal's talk this morning. She ended up with proving, I guess she just proved a theorem which I didn't have in Nuperal, but I think this is how we would say what she proved in Nuperal. So the highlighted part there. So we have a type which is an intersection of a family of types. So that's what that intersection T in type T arrows T would be. So that should be not exactly the same as the for all alpha, alpha arrows alpha, because that's as we've pointed out, an impredicative notion. It's quantifying over all types. This one is only quantifying, it says type there, but that's just a display form, which I'm going to show you. If I explode that, it says it's really universe I. So it's a universe of types with a level parameter I, which can be anything. So it's not quantifying over all types, it's quantifying over all the types in some universe, which is kind of like all the types, but it doesn't put them all into one big bin at the same time. So it's not quite the same type, but still, it's enough. Any function that has that type is going to have the property she said, that given any type t and any member of that type t, x, f of x has to be x. So it has to be the identity function. And the proof there, I just first proved that any two things of that type have to be equal. And then I plugged in, so I just instantiated the lemma that says they have to be equal. I just instantiated the f that I have and the identity function, which does have that type. And then it was easy. So let me just quickly show you the proof that I did of that things of that type have to be unique in that type, because it mirrors exactly the proof that she gave. I just wanted to just show. So actually, I'm gonna start from scratch on this theorem totally and show you how you actually enter the thing, and then so you could try to follow along and type it in. If you have Nuperal running, you could try, but I save that for the next example that we do. Then I'm gonna show you step by step how to create a theorem in Nuperal and prove it. But I just wanted to quickly walk through this one, and I'll show you a little bit of how we do things. So I've got the font here really, really big so that you can see it, which means I don't have any space on my screen, but so it's a little awkward for me. But anyway, here I would come up. This is if you have this up, this is what we call the navigator, and it's got all these buttons on it, and then there's this listing of the theorems you have in some section of your library. So I'm going to come here and say make theorem, and then it says, okay, I want a new theorem, and I'm just going to call it theorem. I'm going to call it free theorem. That's what she was calling it. Free theorem 1. Okay, so that created an object in the library for me named free theorem. Now I'm going to press the right arrow to open that object up, and now it's gone up. Okay, so now I've got this proof editor thing that says, all right, you want a theorem, what should be the goal of the theorem? So now Nuperal doesn't have a parser. It's a structure editor, so you just start entering terms using the names of the operators of the term. So I want to say for all functions of that type, so I want to say all. So I just type all, and that gives me a template for all. And I give a variable name. Now I want the type polymorphic in T arrows T. So that is the intersection type for us. So I say isect. And now I'm going to say T in. Now, this T is now ranging over a universe of types. So the editor alias for that is universe. I could type universe, or I can type uni. That puts in level I. And then the display form we have for universe I, since it's kind of like an arbitrary universe, when we use a variable for the universe level, it means it could be any universe. So universe I just displays as type. Kind of in Coq, if you say type, it's going to pick a universe level for you in the end. So it's kind of similar to that. Okay, so for all types, and then I'm going to say fun, T, arrows T. Okay, so for all F in that type, and now what I'm going to do is I'm going to use the command meta P to go up one level in the structure, and then I'm going to say meta K to copy that, and then I'm going to hit enter, and that'll bring me back to this slide. Yeah?
Is there any kind of standard ASCII format for these?
There's a sort of an exchange format that the database uses, and that's got horrendous numbers of parentheses, and yeah. So you can write tools that will translate. Like we hope to do this, to take Coq expressions and translate them into numeral terms and back and forth. Yeah. So we can do that. Yeah. But yeah, at the user level, we don't. But yeah. Okay. Now I'm going to paste this in. I'm using Control Y. I just did that because I want to also have a G. Now I'm saying Control D, to delete, and then G. All right. Yeah.
You're describing standard Emacs comments because this runs in Emacs?
No, this is our own homegrown proof editor, but since it was certainly influenced by Emacs, like the people who programmed it programmed Lisp using an Emacs interface to program Lisp, and so they just tended to, basically we get to pick any old key bindings we like for these various things, so they tended to pick Emacs-like ones. But is meta K and control K an Emacs thing? Usually it's like W, right? But
you would do control meta K?
Yeah.
Instead of meta K.
Yeah. Anyway, so we're, I think on our FAQ we're going to have a list of all these different things. Yeah, because that's the thing that people hate about a structure editor is you can't really use it that well until you have all those little key bindings kind of like memorized by your fingers. But once you do, you can just zoom around and do stuff. So I don't know. Anyway, equal. So F and G are going to be equal in this type, which I'm just going to come over here and grab. So I'm using meta K and Control Y to cut and paste. Okay, so there's my theorem. So now, the very first time you create a theorem, you can just launch into proving it. But I like to get in the habit of always typing Control meta G, which saves the goal. And the reason for that is if I come back here and I decide, oh, that's not quite the theorem I wanted to prove, if I don't type Control meta G after editing it, it'll still be trying to prove the theorem that I saved in the library the first time. The Control meta G says, overwrite what you were proving with this new thing. So I always do it even the first time, even though there's nothing to overwrite, because I don't want to forget that I have to do that when I edit. So anyway, and that changes the little status at the top there to say, I don't know the status of this theorem. You just created it. So it's saying, I don't know whether it's true or false yet. Anyway, so now I'm going to type the tactic auto. And okay, so over in this box here we have where we type our tactics, and we also have a structure editor for them, but there you can typically write text because most of the tactics are just ML functions that are, have text names. But for the nice ones, the ones we use a lot, we make a little structure editor. So now I hit Control Enter and to run the tactic. Okay, so the auto tactic pulled off the quantifiers. It's like doing intros, and you can actually, Vincent defined. Oops. Well, I thought that was fixed. He defined, some of the Coq names as numeral things. So, so you could also say intros. Anyway, now we're trying to prove that these two things are equal. So inside of this equality is the type that we're trying to prove. We're trying to prove F is equal to G in that intersection type. But typically when you're proving things, just like in Coq, you don't want to see all the type parameters displayed all the time. So we typically don't. The display form for equality doesn't display the type that you're trying to show because you kind of usually know what that is. But sometimes you don't. So in which case you use this is middle click. Middle click sort of explodes the term and shows you all the details. That shows you all the subterms, all the binders, and everything. And then middle click puts it back again. So anyway, so to show that we have to use something about the type. We're trying to show it's in an intersection type. So the tactic for showing two things are equal in some type. What would it be in Coq? You'd use some like constructor, or there's very various things. But anyway, for us, EQ type CD. So C stands for conclusion, H stands for hypothesis, D stands for, do the obvious introduction or elimination rule. When you say D on something, it means do the step that corresponds to that type. So CD stands for D in the conclusion, and then here we're trying to show that two things are equal in some type. So use the rule for equality in a type for that case. So anyway, so EQC type CD. Now that has generated, it says, all right, for an arbitrary type T, you have to show that they're equal in type T arrows T now. So it would really, in this case, it really would be good if the display form showed us the types as we went, because this is a case where it's not obvious what type we're trying to do. But anyway, it also generated us a well-formedness goal to show that type is a well-formed expression. And it picked the type universe prime, which is universe I prime, when prime stands for +1 on universe level. So it already guessed which type we want. So basically in Nuperal we have so many types that type checking is undecidable. So we prove the types as we go, and we as these well-formedness goals get generated, they get labeled with that label WOOF for well-formed, or sometimes OX. Anyway, and we have a little tactic which, the tactic then, in Coq it's a semicolon, so if we can kind of distinguish between those goals that are sort of auxiliary goals. So if I say then A, so I have a little alias, -THA, that puts in the then A, and then I'm going to say then A auto, and it's going to run auto on those auxiliary subgoals. And so, the fact that universe is a member of universe prime is trivial. So, all right, so now we have to prove F is equal to G in this type. So now, the thing that corresponded to what Amal said, she said, you have to pick that relation correctly. This is where you use your brain and say, what relation am I going to use? Well, in Nuperal, any sort of relation on partial equivalence relation on terms corresponds to a type. So basically, we have to pick what type do we want. And I have to do one other thing. We have to use function extensionality right here. Because we're trying to show they're equal from type to type. So we've got T. Now we have an X in T. Now we have to show that f of X is equal to G of X in this type. And now we're going to, so I think the way I did the proof is the reason they're equal is because they're both equal to X. So I'm just going to assert that. And equal, apply fxx in type T equal, apply gxxt. Then I'm going to say then auto. Okay, so it says I have to prove those two things, but if I did, then the fact that they're equal is now trivial, and auto got that. Okay, so now we're down to proving the heart of the matter. F of x is equal to x. So now we're just going to assert, again, let's see, that member f, so f has this polymorphic type, T arrows T for any T, so I'm going to pick a particular type T for that, and I'm going to plug that in. And just like she said, we want that relation that's basically only going to relate that single x to itself. So I can make a type like that in Nuperal. I can use the so-called set type, the set of all z's in T which are equal to x. So that becomes a type that only has x and other things that are equal to x. Okay, so we're going to... So why does f have that type? Well, because it has type T arrows T for any T, and that's a type, so I think auto gets that. All right, so now that f has that type, should be easy to prove that f of x is equal to x, because x is in this type, and then f has to produce something in that same type, so the only thing in there is x. So I think at this point what do I do? I guess I think in order to convince, I mean, this is not the kind of thing we normally are proving, so auto isn't like set up to, maybe, well, I can try auto. I don't think it'll get it though. Oops, I didn't type auto. Oh yeah, here's the thing. You have to not be frightened by these ugly, ugly error messages. You know, as soon as anything fails, it kind of gives like a trace of all the things that were happening. Just ignore that and look at the first line of it, and it'll tell you, you know, unknown ID. The rest of this stuff, it's saying it came out of a refiner that was running on such and such a machine at such and such a time and stuff. You know, that's all, you know, for tracing of, you know, hard to debug bugs. You know, but this is just like normal. And also another key binding you have to know is Control-Shift-, which you know from Emacs, you know. It's like your favorite thing. Undo, 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 you know, and then you can redo, you know, plot with Control-Shift+. You know, so like if you get any messed up looking thing, just undo back to where it was looking good and continue on from there. Okay, so anyway, I think what I have to do here is like you would do in Coq, where you say, you know, you want to generalize something. You want to say, remember this thing as something of, anyway, I think at this point I have to say, generalize the conclusion. So that's gen-concol. Then I give it type. I say equal. I want to generalize the fact that f of x is actually some z in this type right here. Okay. So if I hit that, it's going to make me prove that f actually has that type, but that follows from the type that we have there. And I have to prove that that's actually a type. Auto can prove that. And now I have to prove that z is x, but z is a member of the type of all things that are equal to x. So I think if I say auto, maybe it'll get it. Okay, it does. All right, so there, oops, I'm not quite done. Oh yeah, because I have to prove the same thing about g. So Control meta J jumps you around between all the different sub-goals you have left. So here I want to show you this. I'm going to go over here. I'm going to keep doing meta P until I have got the whole thing highlighted. Now I'm going to do meta K to copy the whole thing. Now I'm going to hit Control meta J to jump back to where I was. Then I'm going to do meta P to get the whole thing highlighted. Then I'm going to do Control Y to paste in the proof I had. So now I've got the whole proof I had, and all I have to do, I think, is change this F to a G. And now I'm going to use Control return runs the tactic you're at, and meta return runs the whole tree that you've pasted in. So I'm going to do meta return, and it didn't quite get it. Okay, so what? Why didn't it get it? Oh, I think I didn't. Oh no, I pasted in the wrong proof. Is that what I? No, this part. Shirt. Why didn't? What's the difference? Oh, what's the difference? Why isn't it not working exactly the same? Well, auto got that part. Oh yeah, I see. It's just that I had more occurrences of F that I needed to change. So in this wasn't the greatest example of cutting and pasting of proofs, but still. Okay, there. Now we jump up to the top, which I do by hitting Control up arrow, and it jumps me up to the top. And now we see a star up at the top, which tells me that everything's proved. Okay, anyway, and you can see that pretty much corresponded to the proof Amal did, because she said, you know, to prove these things, you have to, you know, use the fact that it works for any relation. And, you know, but in Nupril we have so many types that pretty much any relation you can think of could be expressed as a type. And so that by saying we have something that works for all types, we pretty much have the same, you know, roughly the same. Anyway, it's not exactly the same, but, you know, you can see in spirit this proof is the same. I'm not sure I can do that one, though. That one might be a challenge for me. I'm sure I can do the one about bool. You know, alpha arrows bool has got to be a constant. But I'm not sure about this continuation one that she put up. But I'll give it a try. But anyway, okay. So now I just wanted to do that because, you know, she just finished giving that proof, and you know, for simple cases of this kind of parametricity, I guess, it's easy to prove them in Nupril. But I'm not sure for, you know, for every, you know, anyway, it would be, you know, that might be a hint of somebody's dissertation topic to, you know, relate, you know, the different notions of of parametricity, you know, all in NuPerl anyway. So did anybody manage to get NuPerl running? Okay.
It's starting right now.
Yeah. Okay. So I was thinking what I'm going to do is I'm going to, you know, just walk through some really simple things, and if you have it running, you can follow along typing what I'm typing, and if you don't, you can just listen and decide if it's worth your time to get NuPerl starting so that you can do that yourself, you know. And then, like in the hands-on part where I stop talking and everybody just works on stuff, you know, anybody who thought, yeah, I want to be able to do that, they can go talk to the people who have got it working and say, how, you know, help me get it working. So I mean, I think we can like use our collaborative time this afternoon is just like getting NuPerl going on your machine, and then, you know, if you have time, we can, you know, you can try a few simple things. But okay, so what I wanted to do.
Can I ask really quickly,
Yeah.
is this what you're supposed to see when you start, like with Win? It's not
What do you see?
I see like maybe a small subset of it, like the thing at the top, activate, deactivate.
Oh yeah, so it's probably, yeah, so again, my font is so big. I think what you probably see, you should see, is something like that.
Yeah.
Okay, so this is like, so
I
basically,
don't have nearly as many as the possible commands.
the little button,
Make theorem, for example.
yeah, well, see, there's no make theorem, see? Is it there?
I see one there.
Oh, make theorem. You don't see that one?
Yeah. No, I only have like 2 levels.
I think maybe it depends, maybe I think if you start here, so anyway, what this is, you know, kind of like the top level directory structure. So you're going to go into this theories thing, and I think maybe, so each thing has like a little object in it that says what buttons to put up. So maybe, you know, you have to go in the first time in order so that it knows what buttons. It's kind of context sensitive what the buttons are. So if you're going to try this, go in that theory thing, go down to where it says user. And so so going down is just, you know, hitting the down arrow or just, you know, clicking. Then sort of going into a directory is you use the arrow key, the right arrow, just so you sort of going into this directory. So on your thing, you should see these two objects that say re-init user and re-init user plus. So what those are what we call, those are descriptions of the reference environment that you want to be working in. So that would be like in Coq saying, you know, import, you know, require, export, this, that, and the other thing. So in there is a reference environment. It says make a reference environment that contains standard, so standard is a big bunch of stuff that has all sort of number theory, and, you know, it has all of our rules and has all sorts of stuff. So if you start then, so then just, I think if you're on that thing and you come up here and you say, see this button up here, make theory. So if you say make theory, then you just have one slot in there where you have a token. And so this is saying, I'm going to make a theory that's going to import from this init user. So you just make a theory and name it, you know, my theory, or, you know, use your name or something. So I made one CS199. And so it should be, so, okay, so, oh yeah, so is it, do you not have, if you don't have this button?
I have that button, I just don't have
Any,
any text,
oh, I mean, when you clicked on it?
no, that's not there.
Which wait, which thing's not there? The make theory button itself is not there?
Open collector and all the stuff below.
Oh,
It just says code or, code, RE, user, and all that stuff.
that's there. But you don't have any of these buttons up above? Okay, so I think, so that's supposed to be there. Why do I have it and you don't have it? Let's see. I think, probably, there's supposed to be, go out one level and go, see in this section here, let's see, under theories, if you hit this, these arrow things scroll you more, you know, fast or slow. So if you hit the 4 arrows down, it goes all the way to the bottom. There's supposed to be a thing there, property buttons theory. That's like, those are the buttons that you want to see when you're in a theory. If that's there, then it's supposed to then, you know, sort of inherit from that when you go in here, and then you should get all those buttons. If not, I don't know what's going on. Yeah, so this is no. If you don't have any of those buttons, then you're not going to be able to do the next step. Anyway, so I've got to hurry on along here because this is going. So Bob wanted me to, just first show you just a simple theorem that you prove that's, of the form for all something, there exists something, so then we can, prove it constructively and get an extract that we can run. So I wanted to do some simple theorem and show you how we get the extract, and then how you can then go back and prove the theorem slightly differently to get a better, get a more efficient extract and stuff. So the theorem he suggested is this one. I'm going to start all over. I'm going to make a theorem. So this is the theorem he calls the Stamps theorem, but I already put it there, so I'm going to call it Stamps again.
I have a very meta level question.
Okay.
I wasn't here for the first week of the summer school, so I'll ask the students, is it clear what extract means in this context?
Well, I'll show you as we go. But the idea is, when you do a constructive proof, every rule constructs evidence, and so when you've done a complete proof, the complete proof can build up a term which is the evidence for the truth of the statement. Yeah. What? Okay. Yeah. So I'll just say, the format of a rule in NuPerl is to say a sequent is saying given some context H, and you're trying to prove some conclusion, and you're trying to witness it with some extract term, we call it, the witness term. The rules say, well, if you can prove, H prime implies C prime with extract F1, and you can prove H double prime C prime with extract G double prime, then you can then prove this one with some, rules typically say that. To prove this, it's enough to prove these things. And the extracts that you get from those things can be combined in some way to get the extract for the derived thing, yeah. Okay. 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 All right. All right. So anybody who's managed to even pop up a new theorem named any old thing, you can follow along. I think there might be down to like 4 or 5 of you now. But anyway, we're going to type the theorem we're going to try to prove is every number greater than or equal to 8 can be expressed, as the sum of some number of 3s and some number of 5. So we can, you can get any amount of postage, greater than or equal to 8 using only 3-cent stamps and 5-cent stamps. So, this is kind of a trivial theorem, but anyway. So I'm going to say for every n, and just to make it simple, I'm going to say for every natural number and then greater than 8, I'm going to use n plus 8. Okay, so I'm going to say exists an I, that's a natural number. I'm using nat, and then there exists, oops, I typed exist instead of exists. Exists a j, that's a nat, and then I'm going to say equal, and I'm going to say add n plus 8 is equal to add multiply, that's mul, that's the alias, mul 3 times I, mul 5 times j. And what type do I want them to be equal in? Well, I could want them, n plus 8 is a nat, but it's also an int. It doesn't really matter. I'm going to just use int. Okay, so there's my theorem. I'm going to type control meta G just for good measure to save the goal, even though I don't have to the first time. All right. Well, obviously we're going to prove this by induction. I mean, well, there could be different ways. And we could prove it by different induction principles. We could use just the standard induction principle that goes by ones, or we could use the complete induction principle. Let's just use the standard one. So I could say intro and then induction nat ind on n. Okay, I will. Intro. Oops. Yeah, for some reason, lately, the very first time I type in a tactic, it doesn't take, and I have to go back and do it again. I don't know what, that's some new glitch, So if that happens to you, don't despair, just try it again. That's the thing. I've discovered that people who are just willing to try stuff make a lot of progress. People who get freaked out by some occurrence and they don't understand and just freeze up, then they never make any progress with these things. You just don't, just, what's that? What is nat? The type nat is actually, oh yeah, so here's the thing. If you right-click on anything, it'll show the definition of it. So it turns out the nats actually are just the integers greater than or equal to 0. And you say, well, but shouldn't they be an inductive type? Well, in new Perl, we could have done it that way, but new Perl long ago, I don't know, since 20 years ago, decided that we're just going to bring the integers in as primitive concept. So the integers themselves are just sort of constants of the computation system, all of the integers, and addition, multiplication are just built in, and we implement them in Lisp using Lisp's big num package, and so we just put rules saying that they form a commutative ordered ring, and that's all we use about them. So obviously you can build some other ones inductively and prove that they're the same ones, but anyway, we don't bother. So the induction principle on nats is also just a rule. We just say, well, there's an induction principle on nats. So right here, I'm going to say then. So the alias for then, you can type THEN, but I use this editor alias -th. So when you're on any old term and you type another operator, it'll put a template for that other operator, and it'll put the term you were on as the first argument of that. So that may or may not be what you want, but then you can move it around. So if I type, this is the alias for then, I type -th, and it puts my tactic I already had as the first argument of the then, and then you can say, well, in Clock all I would have to do is type a semicolon. But anyway, this is this is a structure editor, so you have to do something. And so anyway, then the tactic I'm going to use is nat ind. Now, in Clock you refer to the hypotheses by their name, which is the the variable name that that declaration is. In new Perl, we refer to them by their number. So we give them both a name and a number. That's because a lot of the hypotheses, they don't really have reasonable names, and we give them ugly names like %7 or something, and so we don't like to use those names. So we use numbers. May or may not be a good idea. You can refer to the numbers as given, or you can refer to the last hypothesis as -1 and the previous one as -2. So you can refer to them positive. Anyway, so now I'm saying nat ind 1, and now I'm going to hit control return to run this. Okay, so there's our normal induction. base case. All right, we have to express 0 plus 8 as 3i plus 5j. So what should I put in there? I'm going to use the tactic inst concal, and I'm going to give, this is like saying exists in Coq. What are they? We need 1, 3, and 1, 5, right? So I'm going to put 1. So again, these things I'm putting in are terms. In order to put a term in, you type Control O if you want to get a term slot with those little corners around, which I like because it kind of shows me where the boundaries are. You can also type Control U and you get a term slot that doesn't have those little corners. Then so that it can look nicer, but I like to use the one with corners just so I'm sure where my term parts end and my other text parts. Anyway, so I said Control O U, and then I have to, for some reason in New Perl we separate items in lists with semicolon rather than comma. I'm not quite sure why. But anyway, 1. And to get off of this slot, you can either click or you can use Control F to move forward. Anyway, so there's that. And we expect that auto should know that 3 plus 5 is 8. And it does. Good. All right. So now we have the inductive case. So we have an expression for n minus 1 plus 8, and we have to get one for n plus 8. So we have to take the expression we have and get it to go up by 1. So the first thing we're going to do is something like you would do in Coq. You would say, I don't know, destruct 3 or something. So if I say D3, then I get my first I, and then I could say D4. But anyway, this is something I use so much. I have a little alias dash EXR, which stands for EX rep D. That says just keep repeatedly D'ing everything in sight, including existentials. So, I mean, it'll D all the it basically just does D of all the ands and the existentials. Okay, so now we have an I and a J that work, and now we have to get it to go up by 1. So now there's various ways. Let's try to bias this towards using 5s if possible. So here's the thing I came up with. We're going to now, I think Adam showed a case where you want to make a case split. So you say, he said destruct on some Boolean expression, which he built using a lemma that says something or other is decidable. So we have that kind of thing. So again, it's so useful. I have a little alias, dash DEC for decide. So I'm going to type in here some proposition that I want to case split on, and this tactic is going to prove that it's decidable and then case split on the result. So I want to case split. So basically, if I've already got 3 3s in there, that's 9, and I can take away the 3 3s and replace it by 2 5s, and that'll make me go up 1. So I'm going to decide on whether I have 3 3s or not. So I'm going to say LE if 3 is less than or equal to I. Then I'm going to type then A auto because, okay, so now it proved that either 3 is less than I or not. It proved that was decidable. So in the case when 3 is less than I, I'm now going to say inst concal and then, so what did I say? I said I'm going to take away the 3 3s, so I'm going to go subtract sub I minus 3, and I'm going to add 2 j's, 2 5s, add j plus 2, and now I'm going to say then auto, and I noticed that auto gets this rather slowly, and the reason is, hey, that's slower than I remember. Okay, but it does get it. So we have a tactic, a decision procedure that's like the omega thing, which it uses the Shostak's soup-inf procedure, and to invoke that one, you use the tactic auto prime, which does auto together with that soup-inf thing, and auto prime gets that much faster. But at the moment, the soup-inf procedure is just a piece of trusted code. Whereas what auto was doing, it was using a different procedure called arith, which actually produces a proof at the level of those primitive ring axioms and everything. So that's why it got it, but rather slower. It actually built a whole primitive proof of it, whereas this auto prime just said, I'm running this decision procedure which we trust, and it's so anyway. So that gives you, I personally I want to get rid of this this trusted thing and always produce proofs. But anyway, okay. So now, if we don't have 3 3s, then since we're bigger than 8, we must have at least 1 5, right? Because if we don't have 3 3s, we've got at most 2 3s, which is 6. So then if we're at least 8, we have at least 1 5. So now in order to go up 1, we can take away the 1 5 and add 2 3s. So inst concal. So in this case, we're going to add, what did I say? We're going to add 2 to the I and subtract 1 from the j. Okay, and then auto. Okay, and again, I should have said auto prime. It's faster, but auto is going to get this. All right. Okay, so now go up to the top and we're done. So we prove for all n there exists an I and a j. So I'm going to show you what the extract that got built for that is, and then I'm going to show you that I don't like it that much, and I'm going to make it slightly better if I have time. I'm going to go on. I'm going to talk until like 3:20 or something like that. Okay. I don't want to, because I want to do something else besides this. This is too trivial. Okay. So that, I guess I'm going to. So I could just show you directly. There's a way to directly access the extract that was built by that, but I have a nicer thing that I always do. So when I want to, if I want to actually compute with the extract of some theorem that I've proved, I do a procedure that I call normalization, or it's based on symbolic execution. So what I do is I always copy. I just hit this copy object, and I say there's my. I'm selecting on the one I just proved. I hit copy object, and then I just give it another name, where I usually put the word ext to say this is going to be the normalized extract of that thing. I open that up, and I say, okay, now I'm going to prove my theorem over again, and the way I'm going to prove it is I'm going to use the extract of the theorem I just proved, but I'm going to compute on that extract to get it in a nicer form. And to do that, I have this little alias, -ne, which stands for, it's actually all it is normalize extract with some parameters, but I just type -ne. So then it says, okay, the extract of some theorem is going to normalize to something. And so I come over here and I click on the theorem I just proved, and then I come over here and hit Control-Y and it pastes it in. So it says the extract of that theorem that I just proved is going to, by symbolic computation, so this is a tactic that's actually doing the proof that the extract that's constructed from that will compute to something. And I could hope to guess what it was, but I don't. I just leave that blank, and then I just hit Enter, and it says, all right, well, you have to prove that that blank is equal to this thing, which is the extract of your theorem. And I said, well, that doesn't give me anywhere. The reason this is, so this term of thing is the name of, is our kind of name for whatever the extract of that theorem is. And by default, every proof you do is constructive, but you don't necessarily want the extract of everything. So you actually have to ask for that. So you right-click on this thing here, and you click on this button, extract required. I need an extract of that, because it doesn't just automatically construct the extracts for every theorem. Actually, we're probably going to change that because it doesn't really cost that much, and we might as well just do it by default. But anyway, at the moment, so now I'm going to run it again. And now there it is. It says it became that. So you can sort of see, so primitive recursion is the iterator for the natural numbers. And primitive recursion is actually just a fixed point. And so this normalization thing has basically unfolded everything. So I say, well, I don't really need to unfold the definition of primitive recursion. So I'm going to come in here where this parameter is. And if you when you're normalizing things, you don't necessarily want like every definition unfolded. So you can come in and list all the different things that you want to leave as abstractions. So if I do that, it says there's the extract. Okay. So there it is. It says to get the number of stamps for n plus 8, you run primitive recursion. It says in the base case you're going to use 1, 1. But what's this triple? 1, 1 axiom. So the reason for that is the statement of our theorem said there exists an I, there exists a j, such that this thing is equal. So we have to give the I, the j, and the witness for the equality. Well, in Nuperal, we have what you call unicity of identity proofs or whatever. There's only one piece of evidence for an equation. If it's true, the evidence is unit. And if it's false, it's void. So that axiom thing is just our name for the single thing that's in the type unit, because we use that for the evidence for all those things that are just sort of, 0 equals 1. I mean, 0 equals 0. Why is that true? What's the evidence for 0 equals 0? We just say axiom. So anyway, because of that, our extract has these extra bits in it that we really don't care about. But anyway, that's we're still getting our I and our j. But so actually, I was going to go through a variation of this and show you how. Well, I'll just do one quick variation, and then I'll leave it at that, because I don't want to use up all my time on this simple example. But I'll just show you. If we come back, I'm going to go back to my theorem here. So here's a very useful command that I use every day. Control meta A. If I type control meta A, that's some sort of a prefix for, I don't know. Here comes some kind of a macro command or something, I don't know. And then I'm going to say PSP. So that, the control meta A is some sort of a generic prefix for, here comes a command. The P is sort of saying something about proofs, and SP stands for scratch proof. So basically so I just have that memorized. Control meta A, PSP, creates me a scratch copy of my proof. So whenever I'm about to modify a proof, I always pop up a scratch copy of my proof. In case I goof up and forget what I had done, I just have it over there. Most of the time I never need it, but I just have it there, and yeah.
Is there any kind of integration of version control systems with Nuperal?
So, yeah, that's I was talking to people at lunch, for your own version control. Well, so basically, Nuperal is this database. Everything I'm doing is just getting committed into the database, and so then you think, what if I committed a change that I don't want and I want to retract it? So there is, like a log of everything, and so like everything that you ever had going way back into the past is still there until we, actually do a major garbage collect to remove them. So in some sense, you can't lose it, but it's not that easy for you. If I do some major goof up like that, I have to ask Rich, get me that object back. I mean, it's in the database. So probably with more user interface stuff for searching the database, we could build it so you could find, previous versions of any object and revert to them. But usually, if I'm planning to make a change, I just make a copy of my thing, and I don't delete the old ones until I'm happy with them, and then then I say, oh, I don't need this old one anymore. But yeah, and so anyway, that's.
So how about coordinating proofs with multiple authors?
Proofs with multiple. So there, we would, typically, sort of divide them up into like lemmas and say, you work on this lemma and I'll work on that lemma. But we can both be working on the same proof, and basically if I do a step and he's also online at the same time, and he'll just see the step that I just did, appear on his editor. So that's kind of cool, but it might freak you out too. So I don't know. Yeah. So but another thing that's nice is if I'm working and I have a question about something, just clicking on a thing, and I can go in our little chat window and just hit Control Y, and that posts a pointer to the thing, and then I can send it into the chat and say, hey, help me with this, and then it pops up on their screen. They click on it, they see exactly what I'm seeing, and they say, oh, you should do this thing. So there's pros and cons to having this sort of automatic sharing all the time. So you'd have, so it works really well for a small group of people that are collaborating. But to open it up to thousands of people around the world, we might have to revise our concept. But I don't. Yeah. Bob's going to say something.
Comment that the one world seminar we couldn't shut down, it just kept going, was when everybody could participate in the proof. So Lori would put up her proof and try to go to the next step, and somebody would fix it. Who did that?
Yeah.
We had this communal activity, and we saw that it was a huge time sink. Everybody, so we had to build in tools to keep that from happening all the time.
People would want to, anyway, so I'm going to quickly, I'm going to come to my stamps theorem, and right here on my second exists, I'm going to explode that, and I'm going to use a different exist that I call SQ exists for squash exist, and that's really just I'll just say that's really just an alias for that set type. So to say there exists an A such that B, if all you want is the A part, you just want the A that exists and you don't care about the evidence for the B. In Calc you would state the B part as in prop, and so that it wouldn't create it. But anyway, this is the way we do it in nuprol. We have this set type. It's basically it's the dependent product of A's together with witnesses for B, such that you just apply pi 1 to that and only project out the first component. That's what the set type actually is. So anyway, so if I just use that type, I have a display form, and so it just says exist J, and then it just puts curly braces around to indicate to you that that's actually just a set of n's such that that thing, it puts curly braces and it uses a slash instead of a dot. So now I'm going to save that goal, and I'm going to replay my proof, and I think the proof goes through unchanged. So remember, auto was kind of slow, so because I didn't use auto prime, so we'll have to wait a little bit. But then, okay, so the squash thing didn't have any effect on the proof. So now I'm going to go back to the extract. So remember, the extract looked like this thing with those extra axioms in, but now if I run it, they should go away because I got rid of them. Why is that slow? It wasn't slow before. Every so when you're using, list-based system, something decides to garbage collect, and take a while. So I don't know what's going on here, though. I'm going to look. So here's all my processes. Oh, okay, that was the refiner. I don't know what slowed it down. Go ahead. Whoop. Extract. Okay. Oh, I see what happened. That it tried to prove it. Oh, I guess I'm going to just say skip. You can put skip around any tactic, and it just turns it into the tactic that does nothing. So you can just sort of see, you think, oh, I don't think I needed this tactic. You can just put skip around it. I think what it was trying to do was finish the proof. I don't know why this is taking longer than before. I did this very thing the other day, and it worked just as. So what is it? Don't know why. Okay, it's working hard, but anyway, it finally. So anyway, when you like the looks of it, you can just paste it in here, and so like here. So now it's saying the extract is let I and %2 be the x that you had from recursion. So I don't know why it picked %2. I don't like that, so I'm going to change it to j because that's just a bound variable, and I can pick whatever bound variables I like. So anyway, then I can. Anyway, there's the extract using the set type to get it nicer. And then what I was going to show you is if you compute with this, you still won't like the results, because if you say, what's the stamps for n equals 100, that'd be express 108 in 3s and 5s, it'll say, well, the first one, it'll say it's a pair of an I and a j, where the first one is something like 108 minus 3 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 minus 3, whatever. Because by default, all applications in new Perl are lazy. In Coq, everything has a value, so it can use lazy or eager, it doesn't matter, and so probably the compiler decides whether to use eager or lazy, and a compiler, when working with numbers, will use eager evaluation. But in new Perl, everything's lazy by default. So if I'd run this thing, it seems like it's using lazy evaluation when it shouldn't. So I was going to show you that you can come back into the proof, and at a certain place you can, in the place where we sort of generalize something, you can do a kind of an evaluate generalize. It says, evaluate this and remember the value. And that puts in a call by value, and we get a nice extract. But I don't have time to do that. I want to do something else. I don't want to spend all my time on this little example. So anyway, you can prove constructive things, get the extract, compute with the extract, decide that you don't like some aspect of it. You can go back in the proof and adjust the proofs in slight ways that don't have much logical difference, but they can improve the extract. So anyway, so that's what we like to do. We like to actually construct programs that we really want to use by this method. So we construct distributed algorithms like Paxos by this method, and we get actual code coming out that's relatively big, and we use these symbolic execution methods to make them a bit faster, and then we run them, and they're not as fast as sort of state-of-the-art handcrafted Paxos, but they're within an order of magnitude. Instead of running at one microsecond per transaction or something, we can get 5 or something. So anyway, with more work, more sort of compiler-like work, like Adam does, we should be able to, get, in principle, there's no reason why proofs, by code constructed by constructive proofs, shouldn't be able to run efficiently, because whatever methods that compilers do to make it efficient, you should be able to incorporate that in your proof somehow. But, we haven't gotten there completely. Okay, I want to show you another example of a theorem that's kind of fun. So I'm going to prove, so here in this, so here's the theorem I'm going to prove. I'm going to call it, let's see, do I have it here? Okay, I'm going to make a new theorem, and I'm going to say type not in type. Okay, so here's my theorem. Not member universe I, that's type, universe I. Now, there's several weird things about this. Let's hit Control G. First of all, in a system like Coq or Agda, you don't even state typing judgments. They're just built into the system. They either hold or they don't, and the type checker tells you. So you can't even prove, directly. You don't state typing judgments. They're built in. So here I'm stating a typing judgment, and then second of all, you think that's not even well formed, no matter what, right? In Coq, if you try to state that, you can sort of state it in some ways, but it's going to fill in the level parameters for you, and it's going to say that first type is in one universe, the second type is necessarily in a different universe. And I'm trying to prove that the reason it's doing that is because they couldn't be in the same universe. I'm trying to, just state that that's the case, that you can prove that otherwise you could prove false. So now I'm going to say auto. Now I think if anybody's following along with me, oops, I'm going to say D0. Okay, so again, the D tactic does the introduction or elimination, and you refer to clauses by their number. So if they're got numbers from 1 to n, they're hypotheses. 0 stands for the conclusion. So D0. Okay, so it says, okay, assuming type is in a type, we have to prove false, but also we have to prove that type in type is at least a proposition, and it's suggesting that it's a proposition at level universe I, but we think, well, that can't be. that's not a well-formed proposition because like normally a typing judgment is not even a proposition unless it's true. But, in fact, auto proves it. So it's not proving that it's true. It's just saying it is a proposition. It could be true or it could be false, but it's saying that it is a well-formed proposition, and I'll tell you why that is. And this is, I think this is a pretty cool thing. So in New Perl, types are partial equivalence relations on terms. So basically, any kind of partial equivalence relation on terms is allowed as long as it preserves. So, you have to preserve what's called definitional equality. But in fact, in New Perl, we preserve another equality that's a little bit stronger called computational equivalence. So Doug Howe defined this relation on terms in a lazy computation system, and we use the symbol squiggle for it. And he defined it in terms of a little larger than that? Okay. Okay. All right. I'm going by the sort of size that, all right. T1 squiggle equal to T2. That stands for, so, intuitively it's saying whatever canonical form T1 computes to, T2 also has to compute to that canonical form, and the subterms of that canonical form have to also be in the squiggle relation. So it's a co-inductive relation on terms. And he defined it actually, so this is bisimulation, and this is simulation. So this says if T1 computes to a canonical form, then so does T2 compute to that same canonical form, like pair or something. And then the subterms also have to be in that relation. So it's a co-inductive relation, and this is just the conjunction of the two. And anyway, in New Perl, all types have to be closed under that relation. Yeah? Yeah. That's right. Yeah, so this is so this thing is defined in terms of the computes to relation. So you have to know what it means to compute in one step and then extend that to computing. Yeah, that's right. That's right. So this relation right now is defined on the computation system that New Perl has, but it satisfies the properties we need only provided certain constraints hold, which they do in New Perl. So we can add more things to the computation system in the future and not mess this up as long as we obey a certain constraints, but we still have to be a little bit careful if we want to add new things, which we have added new things recently. We've added exceptions and so on. Anyway, but this thing is a partial equivalence relation on terms, and so we can make a type which we call base, which is the collection of all terms with squiggle as the equivalence relation. So that's like, so by taking the collection of all terms and saying with this relation as the equality relation, that's a type for us. It's called base. And it turns out that the well-formedness, like when is A equals B in T, when is this a type? Normally, in most type systems, this is a type only if A and B are actually members of T. You can't prove that the equality type, A equals B in T, is a type. You can't prove that that's a type unless you can prove that A and B are actually in T. But it turns out that we can extend the definition, so I can prove that this is a type provided A is in T union base and B is in T union base. So if A is in T and B is in T, then that's good. If A is in T and B is in base, and so on. So we can extend the definition of the equality type to include terms in base. And so that just means that just like a completely closed term is okay, but also a term that's got parameters from a type whose equality is squiggle will also work. So anyway, that's it's a bit technical, but that's why the reason this worked is because type is just a complete, it's just universe I, it's a closed term, so it's in base, and so that's why that was allowed. Yeah.
Can you give me an example of a term that is not in base?
Yeah. Well, so like if, well, so like if you can, like every term, once you come down to the actual, I can't give you like a closed term that's not in base, but but when you're proving things, for all x in T something or other, then you're going to be, in a context where x is in type T and you have to prove something. If the equality on T isn't just squiggle equality, then this variable x, stands for a term, and it says the equality there is not base. So like integers mod 2 are the type of all integers where, if they're equal mod 2, then they're considered equal. So an integer mod 2 would not be in base because the equality is not squiggle equality. So, 2 is not squiggle equal to 4, but 2 is equal to 4 in the type of integers mod 2. So it depends on the context, like what type you're assuming something is, whether it's in base or not. But anyway, okay, so now I gotta, all right. So now we got through. So if you tried that along and you didn't, in auto didn't prove that, it's because as I was preparing this, I realized, oh, auto doesn't prove that. It needs to invoke a certain lemma about equality in base, and it's not doing that, and so I fixed it so that it would. And then I realized that's not going to work for my demo because everyone has their own copy. So we prepared a little patch file that you could load to make it do that, but let's not worry about that now. So that's the pros and cons. Like if we're all sharing the same repository, then any good thing I do is shared by everybody. And if when everybody has their own, then we have to create patch files and pass them around. So, yeah.
So if you're changing mathematics code,
Uh-huh.
does that have a break something like that?
Yeah, so I would say that would be like, presumably in Coq, all those contributed things, if they ever change anything, they make sure it works on all the contributed files before they, make their new release. So far, there's going to be some growing pains if we try to move to a mode where NuPerl is sort of open to the world. We've been sort of, our own little community. I mean, saying NuPerl has been a vehicle for PhD students to do cool things and do research and think of new things, but we haven't been focusing, and we do get funding by doing applications. But again, those are normally a sort of a smallish group of people doing that. So yeah, so you can see there's going to be some issues if we try to move to a mode like Coq where many people. So like normally, yeah, we just have this library of everything that's ever been proved in NuPerl, kind of like, and if I change tactics, I say I think this is going to be a good idea. Then I run everything, and we can run like everything that's ever been proved in NuPerl so far, overnight. Again, we use many machines, like when it's farmed out to 50 or so machines, we can run everything overnight. And so then I see what's broken and I say, okay, that's not very many. I'll fix those and I'll keep that change. And otherwise I'll say, oh, that was a bad idea. So yeah, you can see there's going to be problems. All right, so now we're going to prove this. We're going to prove false from this. So we're going to use Russell's argument. So we're going to assert, whoops, not that kind of an assert. So we're going to define the Russell type. So we're going to say, so Russell's argument is essentially, if it weren't for the paradox, then you could define the type of all types T that are not members of themselves. Now, if I try to prove that that is a type, it won't succeed because the equality on types is not squiggle equality. So I can't use that. But if I say, all right, so this isn't going to work, but if I intersect that with base. So now this is the set of all types in base that are not members of themselves. And I'm going to claim that that's actually a type. And I think now Otto gets that. Okay, so now why should that be? So for that to be a type, T intersect base has to be a type, and then for any T that's in type intersect base, T in T has to be well formed. Well, but since it's in base, by that same argument it is. So this is, and then it also has to be in universe I. And why is that? Type is not in universe I, but I've assumed it is. So, under the assumption that type is in type, this thing actually comes out in universe I. And, if you tried to, without this assumption here, yeah, so let's see, if I temporarily take that away, thin 1, and now I try to prove this, it's going to say, you have to prove that type intersect base is a type. So you have to prove that that's in universe, so this is, what I'm trying to show is impossible. This is not true, but I'm assuming that it is true in order to show that it's false. So, so under the assumption that type is a type, this Russell type then becomes a type also in universe I, and we're going to get a contradiction from that because we're going to do the Russell argument. We're going to first show that it's not a member of itself, and then because it's not a member of itself, it is a member of itself. So first, now we're going to assert that it's not the case that this Russell type is a member of itself. D0, then Otto. Okay, assuming that it is a member of itself, we have to prove false. But by definition, this thing is the set of all things that are not members of themselves. So if it were a member of itself, that's a contradiction. So I think I just have to say, for some reason, when I did this before, I had to say unfold member in hypothesis 3. So now it says it's equal to itself in that, and then I said EQ type HD this time for hypothesis in 3. So again, scary message, but just ignore that. Then Otto. Okay, so in order for these two things to be equal in the type of things that are in type arrows base, intersect base such that T is not a member of T, I have to show that to be equal in this type. Let's see, it's gone off the screen for me. To be equal in that, how did it get that? To show, I'm trying to show that this is not a member, that this is a member of its. Does anybody understand that? I understood it at the time I did it, but it's like, this is, it's a paradox, so it's kind of confusing. So I'm saying, okay, assuming, oh wait, I see. No, the assumption that this is a member of this type means that it's not a member of itself. Yeah, I see. So the meaning of this assumption is that this type, this Russell type, is not a member of itself. That's what that says. But here, by hypothesis, it is a member of itself. So I guess by unfolding that and saying what it means, then we see that there's a contradiction, and so we can prove anything. So I guess that's how that works. We can come back, if we have time, we can come back to that, but I don't think we have time, so I just want to finish this. So now we have that the Russell thing is not a member of itself, but then by definition, it is a member of itself, because it consists of all those things that are not members of themselves. So now we're going to assert that it is a member of itself. So I guess we're going to assert this. Now, to do that, we have to do mem type CD. Oops, I didn't say mem. Okay, so we have to prove that it is a type in base, but we already established that it was a type. I mean, that Otto can prove that. And we have to prove that it's not a member of itself, but that's what we just proved. So we have that as by hypothesis, so Otto gets that. And then we have to prove that that's a well-formed type, but we saw that because it's in base, it is. So anyway, now we have, it's not a member of itself, and it is a member of itself, so I guess Otto sees that there's a contradiction there and finishes the proof. So there's a proof that type is not a member of type, that actually works, inside the theory we can prove that. Obviously in the meta theory you can prove that, but here we've proved it inside the theory. Yeah. Okay, the role of intersect base was because if I tried to just define Russell, is this the right kind of marker? Whiteboard, okay, I didn't want to, it seems so black. If I tried to define Russell as the set of T in universe such that not T in T, I need, in order to get this proof to work, I would have to prove that Russell was in, under the assumption that universe I is a member of universe I, the false assumption that that's, I would have to prove that Russell was a member of universe I in order to get this thing to working. So to do that, it would say, okay, well, you have to prove that universe I is a member of universe I, which we have by assumption. But then I would also have to prove that this predicate in here was also a proposition at level I. And the thing is, without the base thing, the rule we have is this is a proposition if this would only be a proposition if this T was either in T or in base. And if I don't assume it's in base, then I would have to prove that T was a member of T. So this would only be a proposition if every T in UI was a member of itself, which it's not true. So in other words, it's to get this thing, which Koch wouldn't even would say you're not making any sense at all with this. In order to allow Nuprol to say, yeah, it makes a little bit of sense, we have to have this intersect base thing. So it's just, this is kind of just a curiosity in a way, but I think it's nice that we can actually do some of these things which you'd normally just have to do in the meta theory. We can see them right in the theory itself. I mean, this doesn't have any. If I showed you the extract of that, it's a negation, and so it has no computational content, and it's a well-known fact that type is not a member of type. So why do I need to prove it? But it's just it's just there's a bunch of things we can prove inside of Nuprol. So next time I'll show you. Bob's going to talk about the fact that we have types that contain diverging elements, and so because of that, for things in base, for T in base, whether or not T converges to a value, which we just write T down arrow, has a value to, this thing, whether or not T has a value, is a proposition. It's a well-formed proposition on base. That's because on base, the equality is squiggly equality, and by definition, squiggly equality preserves computing to a value. So if anything in base, it either computes, in the meta-theoretically anyway, whether or not it computes to a value is a well-formed proposition. It's not decidable though, because of the halting problem. And so we can, I'll show you, we can do an internal proof of the undecidability of the halting problem. So we can explicitly construct a statement in Nuprol that contradicts P or not P. So because of the rules of Nuprol and because of partial types at least, if not other things, we explicitly contradict classical mathematics. So we're not consistent with P or not P. In Koch, in the prop model, you can work with P or not P, and Georges Gonthier used that in his proof of the four-color theorem. He used the classical reasoning, but in Nuprol, we've put in too many other things, too many other principles, Brouwerian principles, and so anyway, we actually contradict P or not P. So we can show that explicitly. I'll show you that next time. But anyway, I think I'm going to stop saying things now, and then. So so now the idea is you're going to hang around and do stuff, and I can, if anybody wants to try to do something in Nuprol on your own, I can walk around and if you want to propose doing something, I could walk around and see what you're trying to do. Like one thing you could try to do is prove. You could try to prove this theorem if you can manage to enter it. For every x that's a natural number, there exists an r, which is a natural number, I guess, such that r squared is less than or equal to x, and x is strictly less than r plus 1 squared. Okay? So there, that's kind of similar to the stamps thing. I'm saying for every something there exists something. So this is called the integer square root. You could try to prove that, by similar method. It's not that hard. I mean, so you're trying to prove for every natural number you can find something which is the closest integer to the square root of that number. It's a number whose square is at most x, but if you go up one more, it's bigger than x. So you could try to prove that theorem. And the thing that's interesting about this one is if you prove it like the way I did for the stamps thing by just the regular induction principle on the natural numbers, you're going to get a horrible algorithm for the integer square root. It's going to start with the number, and it's going to compute the integer square root of x minus 1, and to do that it's going to compute the integer square root of x minus 2, and so on, and then adjust. It's going to go all the way back to nothing and build up the square roots one at a time, and then adjust them until they work. And there's a way better algorithm. So another thing would be, can you discover the way better algorithm and figure out how to prove it? Because if we use the way better algorithm, okay, I'm just going to show you one teeny weeny thing here. If you discover the way better algorithm for the integer square root, so in this is a thing called the top loop where we can just evaluate commands. So one of the commands is view show C for computation, and for some reason it wants me to just put a label on the window. Doesn't really matter, I'll just call it comp. Then you can put in a term here. So I'll just evaluate this. Okay, now, on this giant font, it popped up somewhere on my screen, but where? I can't see it. Somewhere. Normally, I have the font normally set so that everything that pops up is, anyway, somewhere. It should have popped up a window. Maybe I typed it wrong. View show C. View none. Why did it not work? Is it failing? Anyway, I wanted to show you that I think it must be somewhere on my screen, but I just don't. Well, there it is. I've popped up two of them. There's somewhere on my screen, but I can't find them because I made the. Oh, here it is. Okay. Popped up this little interface to the computation system. So I'm going to say, so I have this. So using Bishop's definition of constructive real numbers, we constructed the real numbers, and it's pretty much the same as the Corn library in Coq. The same basic principle. So if I want 10 decimal digits of the real square root of the integer turned into a real of 2, so there's the real square root of 2, and I say compute all. Whoop! Wait, I did something wrong. 10 decimal digits. Why did this? This always works. I must have the wrong. Okay. I have a more general. So now this is the square root. This has to work. Ah! Something. Oh well, that's spoiling my demo here, but I must be somehow getting the wrong. I see. Somehow, I think I know. Well, anyway, I'll do it later. Anyway, I just wanted to show you, but it's not working at the moment for some reason. I must be in the wrong reference environment or something. I'll have to figure it out. But anyway, using just that simple algorithm for the integer square root, if you get a good version of that, you can turn it into a good version of the square root function on the reals. And so I have, using that, I made a version of the square root on the reals that, if I say, give me 1,000 digits of the square root of 2, it just goes and prints them out. And if I were using the bad version of that, it would take, the lifetime of the universe to do that. So, so there's a way of getting that square root thing efficient if you can discover it. But anyway, so I think I should stop here, and then we can hang around as much as, if anybody wants to, those people who did manage to get Nuperal working, they could help the people who really want to get it working and say what worked for them to get it working. And then if anybody wants me to come around and, if you want to just try to state that theorem and start proving it, and you say, what do I do at this pot? Then I can come and help. And another thing you can do, in your own time is if you have this thing working, we've given you much of the Nuperal library. So there's tons of stuff in there. There's, all that theory about reals, everything up to Taylor's theorem, and I started, Bob Harper wants me to formalize that paper by Cocan and Besem and Huber on the cubical sets model of homotopy type theory, and I'm like, well, I don't know if I'm halfway through or not. I've proved many of the pages of that paper up to the part where I have to prove that the nerve of a groupoid is a uniform can complex, and I've proved all of that. And if anybody knows about what all that is and they want to see it, you can go and look in there. I've got some basic category theory and the Oneida lemma and all that stuff. And I didn't know what any of that stuff really was. I just sort of go look on the NCATLab page and type in the definitions and go through that paper, and they claim something, and then I just prove it in Nuperal. So it's working. So I've got all that stuff there. Cubical set model of type theory is there. I'm up to the part where you have to prove that the definition of the universe in cubical sets forms a can complex. So that, in Huber's thesis, goes on for about 15 pages. And my productivity in formalizing this is about a page a week. So I'm kind of bogged down on that part, because 15 pages is 15 weeks work. That's kind of like that. But anyway, that's there, and there's tons. There's just so you can just browse around and see what's there, and then look at the tactics that are used to prove those, and try to guess how they work. But we put on our FAQ page a kind of a little side-by-side listing of the workhorse tactics of Coq and what the corresponding thing in Nuperal would be. And so if you already know the tactics you would use in Coq, you can kind of use that as a guide to figure out what to use in Nuperal. And then there's a more detailed user manual on the website that's 100 pages long, and you could start reading that if you have questions. So anyway, we can do that, I guess. So all right. So yeah, questions. Yeah. Okay.
Yeah, you can mention the design choice of making one monolithic system. I mean, looking at it, it looks like there's more than an operating system around this.
An operating system? So maybe when we can ask Bob about that. But what sense do you think it's monolithic?
I mean, you have this state that includes a chat as well as an editor, as well as
Oh,
as well as
I see. Rather than sort of providing a kind of a spec of a proof engine and saying let other people write their own
no, you
tools.
can write them as separate tools. For
Yeah.
example, I mean, it seems that I need to learn a whole set of key bindings to be able to write proofs. These seem like two very separate.
Yeah, well, see, so Nuperal's been in existence for 25, 30 years, so we didn't have any of that stuff then, so I mean, there was no proof general or anything, so this editor that you're looking at has been like this for, ever since I started working with Nuperal, which was 1999 or something, so it was already there, so yeah, so it's you could say, so we already had all this stuff going, and then, Coq came along with all these other things, and so we could have said, we should adapt to that.
No, but it also, I mean,
Yeah.
Coq is not tied to proof general. If
No.
proof general dies tomorrow, Coq is still usable. The existing
Yeah.
tutorial, you can see the files.
Yeah.
This doesn't seem to have a notion of files or anything.
Well, the Nuperal 4 did, but then, so I'm not sure, you'd have to, NuProl 5, this is NuProl 5. It had already been created before I started working with it, and so they decided, I don't know, you have to just, what was the rationale to build NuProl 5 the way it is? With a database, and I mean, the database aspect of it, I mean, as Adam was asking, is there an ASCII exchange format? There is, so we could build, the database part could serve up content to other tools that people would write. Yeah, so it's just, the thing is, NuProl's been, as I said, a research vehicle for, many, many amazing students to, learn, amazing things about type theory, but it hasn't been focused on a production environment, but it probably needs to be, because otherwise, it's just going to fade away. So, we probably need, to address these issues of usability so that, if people like it, they can use it, but. What's that?
Without a 16 gigabyte VM.
Well, that's the thing. You don't normally run it in a VM. I mean, it runs in the cloud, and you just log on to that cloud. So this is the way we brought it for this class, because.
That does not sound scalable.
What's that?
Running it in the cloud on whatever server that you currently have it on that maybe could handle this room.
Well, you don't think that? Well, why shouldn't it be?
I mean, it doesn't scale for 100 people right now. It runs in the cloud. It's not expensive.
It would. Well, it probably would be fine if everybody were, if we had an Ethernet connection for everybody. I mean, we were just worried about the wireless bandwidth. If everybody were just logged on to Cornell through a wireless connection, we just didn't think the bandwidth in this room would. Yeah, it might have worked. This VM thing didn't really work out too good. I admit that. Yeah. Yeah. I mean, we were hoping. Yeah. So that maybe next time we try it, we should probably just do it that way, because this was an experiment, and it didn't really work out that well. I admit that, because people didn't manage to install it very well. Does it take 16 gigabytes?
Yes.
The big one?
Yep. Or no, the small one, light, unpacks the 16 gigabytes.
Oh, of disk space, you mean?
Yeah, after 5 gigabytes.
Yeah.
you download.
Oh, I see. Yeah. Yeah. Is that?
Picking up 21 on my machine.
Is that? Yeah. Well, that's like. The light one is not that much lighter than the other one. I mean, I'm just saying, because I wanted to give you all these NuProl libraries, all the number theory, all the cubicles type, basically pretty much everything we've ever proved in NuProl, except for a big chunk of where we have a whole theory of distributed algorithms and stuff. We took that away, because we thought, well, we probably don't need that to play around with. So I think the non-light one is only, 50% bigger at most, so it's not. What's that? Well, because we store lots and lots of information in the library. So in Coq, you have the files, and if you want to see what state you were in at a certain place in a proof, you load the file and you scroll down to that proof and replay up to that. But in NuProl, we basically every time I did one of those steps and I got the new goal, that inference is in the library. And so we can use all of those partial inferences as a big database to do machine learning on, and also, we have all that information in there. So there's pros and cons of saving all that much information, but we have all of each individual inference is there. And so so it's especially good when you're debugging. You change some tactics, or you change the statement of your theorem a little bit, and you replay and your proof breaks, and then you say, well, what's that? Yeah, when you say, yeah, so you replay the new proof, but you have the old proof, and you can examine, where you were, at this place in my proof that's now broken. I can go and look at exactly what sub-goals and everything I had in my old proof, Whereas if you're, obviously in Coq you could, have your two versions, and you could run your old version in this one. I don't, obviously you can do all these things, but just having this big database of all this information, we find it useful, but then again, it takes up a lot of memory. But it's just a big database of stuff. It can be used for, we're hoping to use it for machine learning and, all sorts of things. We're thinking it's just a big repository of formalized reasoning, down to the level of, individual, it doesn't save the individual rules. A tactic generates a primitive proof at the level of rules, but, it saves at the level of, here's what I was looking at, and I typed this tactic, and this is what I got. All of those inferences are saved in the library, so that's part of it. Also, lots of old versions of things that, that you might want to go back to. I don't know. It's just a big repository of a lot of stuff. So, I know. Yeah.
Can you point to a succinct description of how to use the structure editor? Because that's where I'm
Okay.
stuck right now.
So I guess I don't know for sure. On the website, there's a new Perl 5 user manual, and I don't know how succinct it is, but anyway. And then Rich is, starting to add this FAQ page, but I don't know whether he, so basically what you should do is send a message, to Cornell saying, I need a succinct description of this thing. Send it to, like Vincent Raleigh has been trying to help out. So send a message to Vincent, and he will quickly compose such a thing and put it on that FAQ page, because he's great, so yeah.
You mentioned using machine learning to sort of look at how people interact with the Perl. Have you found anything interesting doing that?
Well, so let's see. No, we had one guy who you probably met, JB. What's his name? And he tried to do a little machine learning. We think that machine learning is going to be a good thing to learn off of this basic, this huge corpus of information. But what he tried to do was just run a simple what do they call it? Support vector thing. To try to kind of classify. He was trying to say, could you, given the goal you were looking at, could you sort of predict what the tactic that the expert, assuming that the proofs that are in there were created by experts, let's say, if it's a complete proof, then in some sense it's an expert did it, because it worked. Whether it's the best proof or not is one thing. But anyway, so trying to learn off what people have done in the past, could you make something that would predict, given this thing, what's the next tactic to try? And then because it could be like a recommender, say, well, based on the features that I see your sequence has, other people tend to use these tactics, and then, that would be useful. So he got something that, worked better than random, but it wasn't that great. Because I think because he was just using, as a feature set, just kind of like, the operators that were present. And to me, that's wrong. What matters is like, which things kind of, you need to take matching into account. Like this conclusion, there's some notion of this thing matches this hypothesis, so therefore, you should use that hypothesis, or, this thing matches this lemma. Whether or not it mentions the same symbols. I mean, that's a first crude approximation. But I think, if somebody can, I think it's, a really great research project to come up with the right, I think, for mathematics, the features that machine learning should key off of are more than just superficial things. There's some sort of structured features or something. I don't know. I just have a feeling somebody could come up with something good, and if we did, we would build it into our proof assistant as a helper. And it might annoy you like the paperclip in Microsoft. You say constantly popping up. I think you should try this, but but it might. If you can say no, don't bother me unless you've run it yourself in the background and you actually came up with a complete proof. But that would be a good mode. You're doing something interactively. The proof assistant is trying in the background to just come up with a proof, and if it finds it, it could pop up and say, hey, you can stop thinking. I found a proof. That would be good, I think. Yeah.
Are you aware of the effort at Dundee University for machine learning for proof general?
Yeah, I think we saw that. Yeah. So that would. Yeah. So if they have any like general principles that we could sort of say apply to the the new Perl corpus. Yeah. So I mean, yeah. The thing is, I'm saying it's a great project. We don't have anybody who's trying to do it, but we think that the new Perl database could be, if they say, okay, we've come up with this great thing and it works well on these things, let's see if it applies generally to this type of thing, then they could try it out on the new Perl database and see if they, we could help with an effort like that. There's, yeah.
So, Mark, one thing to say about our digital libraries, for about 7 years or so, we were funded by NSF's digital library project, and they didn't want a file system. They wanted to understand what would a full corpus of all mathematics organized as a digital library be like. And they were worried about questions like security, naming conflicts at a huge scale. And they provided a lot of funding for us to build it that way.
Uh-huh.
And, machine learning came up as
Yeah.
another option for a database. So this is how we were funded.
Yeah,
to build
but
it.
you'd already built NuPro 5 before that, in this database mode, and I think,
So that database mode was motivated
by that project, yeah.
digital library work. And the papers, Stuart Allen and Laurie Luigo
Yeah.
and John Kleinberg, they all studied, how would you use this digital library to find the key lemma,
Yeah.
result. So they did this on Gontier's proofs and discovered something pretty interesting, that there were like 3 lemmas that he used for everything. And it would have been very hard to discover that, I think, in the other formats. It was automatic.
So what they took Gontier's cock proofs and they broke them up into kind of inferences the way. How did they do that?
I don't know. It's in their paper.
Yeah.
I don't remember all the
Anyway,
details, but it's in the paper they wrote about it.
yeah. So I want to mention another thing. It's mentioned on the website, but if you are looking at NuPro and you say, well, okay, I kind of get a rough idea about what it is, but what is it really? You want to get down to the, what is the semantics of NuPro? I mean, is it based on some kind of a strong normalization proof? No. Is it, what is it based on? What, why do you believe it's sound? And, what is the semantics of NuPro? And, what is it really? What are all the rules and everything? So that's all described in the user manual to some degree, and it's described in the NuPro book, which is, 15, 20 years old now, the semantics of NuPro. But Vincent Raleigh and Abhishek Anand, Abhishek was here at this summer school 2 years ago, I think, 2 summers ago, maybe 3. Anyway, they have done this massive project of taking all the PhD theses, from the past that describe what the semantics of NuPro are and, all these different things, and they formalized it all in Coq. And so there's this giant, and Vincent is just now in the process of, building an official makefile for all of that so he can submit it to the Coq repository as a contribution. It's many thousands of lines of Coq. It's all of Stuart Allen's thesis on semantics of type theory that became, the basis for inductive recursive definitions, and it's all the work of Carl Crary on partial types, and it's an immense amount of work. But anyway, so you probably don't want to just go delving into that, but it can answer every question about what NuPro actually is, because you've got the formal definition of what it, what the type system is, what the computation system is, what's the meaning of a NuPro sequence, what does it mean for a rule to be true, and proofs that all the rules of NuPro, not all of the rules, we're still working on it, but proofs that most of the rules are, I don't know how far along we are, but anyway, eventually we're going to have every rule of NuPro, proved in this sense. So then we'll have an internal sound, a proof that NuPro is sound relative to Coq. If Coq is sound, then NuPro is sound, and then presumably we can go the other way around, except that we can't beat Gödel's theorem. So, so Vincent. Well, what you could do is, here's what I think you can do. In Coq, in one universe of Coq, in universe 2 of Coq, you can make a model of universe 1 of NuPro. And then in universe 3 of Coq, you can make a model of universe 2 of NuPro, and so on. So to show that any number of universes of NuPro are consistent, you can use a big enough universe inside of Coq. Or you can do the whole thing inside of prop, the impredicative universe of Coq, and show that they're all consistent. Okay, I mean all together, the whole type system of nuperal, all the universes. So that's what Abhishek and Vincent did. Okay, now to go the other way around, if I want to show that Coq is consistent inside of nuperal, I have to build the Coq type system, so I have to build the inductive construction of Coq. And in nuperal, we can do it using bar induction, Brouwer's principle of bar induction. So then we could prove that nuperal can be proved sound inside of Coq. Nuperal minus bar induction can be proved sound inside of Coq, and then Coq can be proved sound inside of nuperal plus bar induction. So then you say, well, now how about nuperal plus bar induction? Where are we going to prove that? That can be proved sound inside of Coq's prop model if you assume P or not P. So now you go to classical reasoning, and then you say, well, why do we believe that classical mathematics is sound? Got to stop somewhere. We say, well, nobody's found a contradiction yet. In class. But obviously we can't beat Gödel's theorem, so we can't. There's no way we can prove the system sound in itself. But each thing can be proved sound by adding one more. So like to go from Coq into nuperal, if we add bar induction, we can do it. Then to get bar induction, we can use classical reasoning inside of. So anyway, that's like a project we're working on, and they don't really prove that the things are true. That's up to your philosophy, sort of. But they at least prove that they're sound. Unless this other thing is, unless the whole thing collapses. Yeah. Yeah, no. So we wouldn't. Yeah. So we wouldn't model. We would model the predicative part of Coq in nuperal. Yeah, we wouldn't. Yeah. So I don't know. Maybe. So one thing that's been interesting about this is many years ago, Bob's student Max Mendler created a very powerful inductive type in nuperal that we called the rect type. It's an impredicative recursive type. It just says that there's a fixed point for any monotone function from types to types. So if you can prove if A is a subtype of B, then f of A is a subtype of f of B, then there's a fixed point for that. And that goes beyond Coq's inductive construction, because Coq has a this positivity construct. Anyway, so that thing is called the Mendler type now. People call it that. And he gave a proof of soundness of that was very tricky. It was kind of a forcing argument, and it also depended on strong normalization, which nuperal had at that time, but it doesn't have anymore. So at the moment, we don't know how to prove Mendler rect type is sound. So we actually took it out. It used to be a part of nuperal, but we took it out. We don't need it for anything we do. We build up all of our inductive types. That's something I might talk about tomorrow. Or sorry, when am I talking? I think tomorrow. I'm going to show you how we build lists. I'll show you that. But anyway, we actually build up the data types by first building a co-recursive type using our intersection type, and then we get the well-founded part by building a function that terminates on the well-founded part. And so anyway, it's kind of interesting. So we basically build up the induction principle on most inductive types just from the induction principle on natural numbers. That's all we really need for 99%. But then if we want infinitary types, like in Coq's inductive type, we need W types. And we have a way to build them using bar induction as the induction principle. So by starting with natural number induction, we can get 99% of everything in nuperal. And then if we want to go to things like ordinals and such, we use bar induction. So anyway, so we have that. So we don't need the Mendler type anymore. But I have a feeling that the Mendler type might be powerful enough to do the prop, because it's impredicative. It might be powerful enough. So but then again, we'd need a model of the Mendler type somewhere. But anyway, so that's why I'm telling you, nuperal, is a very, very rich theory. It's got a lot of stuff in it that you can get your hands on and work with. But there's, so basically there's enough detail in the model of nuperal to answer many questions that you might have about a type theory. Like, does Brouwer's continuity principle hold? Yes, we've proved that. Does, bar induction? We proved the soundness of one version of bar induction. There's more powerful versions of bar induction that we are still working on. But most basic questions about a type theory can be answered by this model. But there's still many other questions that go beyond that we don't know the answer to. And so if you're intrigued by those kind of questions, you could imagine taking that model that Abhishek and Vincent made of new Pearl in Coq and adding new features and trying to see can you go beyond. I think we have a very, 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 very rich theory that's there that can possibly be extended in different ways, into the realm of more powerful induction. Can we get more powerful induction principles, or whatever, I don't know. Can we get a model of impredicative types inside of a system like that? I don't know. We don't know. So I think there's lots of very, very intriguing questions for people to work on if they want to. Yeah.
So one of the things Adam was talking about
Yeah.
is like, what's the size of your trusted code base? And what's
So-
the size of your trusted code base?
In lines of code.
Or just you could generalize.
So our goal with this new Pearl and Coq thing is, so essentially, what new Pearl, when new Pearl builds a proof, yeah. So we don't build a proof term and then have a type checker. That's very nice, but since we don't have decidable type checking, that doesn't work for us. So we build a primitive inference tree, of rules. So the refiner, the definition of a rule is, like all these rules you've seen. So we have the rules as each rule is just like a pattern matching thing. Says if you match this pattern, then it's enough to prove these things. So those things have all been, well, not all, but eventually we will have them all proved in Coq. Okay, so what we could do is we could actually, if we do what Adam is saying, we could then translate those objects that have been proved correct in Coq into new Pearl terms. So then we would have to trust that. This translator would just be a transliterator, just saying, you always have the problem. If you prove a theorem, then how do you know for sure that this is really the same as the theorem that you stated in your paper? You could have made a typo. So if we translate all the rules that have been proved correct in Coq and make them be the rules that new Pearl is actually matching, so then we wouldn't have to trust that. But then we still have to trust the definition of a rule says if it matches this, then you generate these things. So the code that actually does matching, has to be right, But that's not very big, Okay, so we'd have to trust that. And then, essentially, then the way we, so then the tactic mechanism, says it builds up. These primitive trees are not actually stored in the library, but the tactic mechanism, is an abstract thing that says, I'm not saying that you have a proof unless you actually did build them. I checked them and then I threw them away. So I think, if you trusted. So there'd be like a little abstract type that's used to implement the tactic mechanism. You'd have to trust that was correct, I guess. And then, so anyway, that's what what Vincent is hoping is that we could actually take the Coq proof of the correctness and take the matching, the definition of what matching, it comes down to second order matching, I think. We could take the definition in Coq of what that is and actually extract from that the actual matcher. In some sense, we should be able to extract from our correctness proof in Coq. We should actually be able to extract an implementation of new Pearl. So then we would be trusting the relation between Coq proof terms and how they get implemented in OCaml or something. I don't know. So there's lots of ways, and of course, if we do it in multiple ways and we never notice any anomalies, then we get more confidence just because we're doing it in lots of different ways and nothing is going wrong. So. Yeah, but right now we are trusting the correctness of all of new Pearl's rules until we've got them all proved in Coq. And I would say we're maybe 50% done. So in particular, one of the rules is that supinf procedure that does the linear arithmetic. So I should, I'm planning to just, the omega thing will at least produce a proof term for it. I don't know if that would be enough for me to, I need to find a proof-producing version of that that's out there somewhere, like in the SMT community or something that produces a proof that's down at the level of ring axioms. Then I can just, implement it, in numerals. So, there's a few. In the past, we had 3 decision procedures that we trusted. One was for just simple equality reasoning. One was for simple arithmetic reasoning. And then supinf was for more powerful arithmetic reasoning. And I've gotten rid of the first 2. I just use them, and they produce proofs, and then I generate the primitive proofs. So those are gone, and that supinf is still there. So that's going to be a project for me to get rid of that, because really, that will, if I keep it in there, that'll be a piece of things, that code that we have to trust, and I don't want that. But we should be able to actually sort of extract from our nuperal and cock proof another implementation of nuperal, and then it might be, if it's too slow, we could like use it as a, if somebody says, okay, you've proved this in nuperal, but I'm not convinced that nuperal is correct, we could say, okay, we're going to run, nuperal will produce a primitive proof. We're going to run that through the cock implementation and check it again, and it's going to certify it again. And so now you have to believe there's a bug in both the cock one and the nuperal one if you don't believe this proof. So, we can increase the confidence that way. So, I think that's the way Vincent has it. That really, trying to get everything down. Okay, there's also the computation system is parameterized by the library of definitions, right? What computation means depends on what the definitions are. And so, in the cock model, there's this. The library is just a big table of mappings between names and values, and of course, on the nuperal side, it's this database. So you'd have to believe that this abstract picture of a database as just a mapping between keys and values is actually what our database is actually doing. So, but again, that's like kind of fundamental. If there were a bug with that, so like somebody could put a Trojan horse into nuperal that says, do everything correctly except if they use this particular term and then do this bogus thing and give me a proof of false, and they could have seeded our code with a hidden error that we've never discovered, in years of use, But anyway, yeah.
Can I suggest
Yeah.
we take a more conversation offline?
Sure.
Yeah.
Yeah. Okay.